Welcome back. Today we're going to consider the difference between kinetics and thermodynamics when it comes to a reaction. So we have this, the Gibbs free energy equation, which, as we had before, describes the thermodynamics of a reaction, whether it will happen if delta G, the Gibbs free energy, is negative by convention. Then the reaction will go because the entropy of both the surroundings, which is in this term, and the reaction, which is in this term, increase. That enables us to predict which reactions will go, but it doesn't enable us to predict how fast they go or whether they always go. This other equation is the Arrhenius Equation, which is, or at least originally was, an empirical equation. Empirical means the same as the laws of thermodynamics, that it was initially developed as an equation to describe reality, but not from any principles. So it just fits reality and doesn't actually describe anything fundamental. Later, the fundamentals were researched more thoroughly. What it tells us is the rate of a reaction is dependent on some number, which we don't know what is, multiplied by the exponential, so E, which is the natural number, to the power of a negative number, minus the activation energy, which is some new energy, divided by RT. R is a constant and T is the temperature. R is the ideal gas constant. It's the same constant that comes out of the ideal gas equation, for example. And if we do the activation energy per molecule, then R changes to K because R is a value in moles. What we can see is both reactions are dependent on T, the temperature, which is obviously a bit of a pain because we're going to see an effect in both. As we have here, if we increase the temperature, then the rate is going to increase, because although the temperature is on the bottom, so when it gets bigger, this part, so this number gets smaller because it's negative, then e to the negative something is going to be less than 1. It's going to get closer to 1. So A will be the reaction rate when this gets up close to 1. If you look at the demonstration of this that I have, we have a reaction which is silane, SiH4, plus oxygen, which turns into a silicon dioxide and water. And we have methane, which is CH4, plus oxygen, which gives us also water and carbon dioxide in that case. What we have from the reaction, thermodynamics, is that it should go in both cases. That's all it tells us. It also gives us a number for how much heat is given out from the reaction. And they both give out quite a lot of heat. So when we set the reaction off, it gets hot and continues. What is not there is the activation energy. So if we take these practically, this is methane, and if we take a standard lighter, I don't have one right here, and we try to light it, or we just let some methane out into the air, nothing happens. We need to light the spark, we need to set off some kind of spark in order to get it to catch on fire. That is because we have to heat up locally to a temperature where the reaction can go. There's another factor in here that we have to think about in a moment. This reaction here is not like that. The molecule pretty much falls apart on its own. So at room temperature, as soon as this comes into contact with air, it bursts into flames. That's because, from this point of view, from this equation's point of view, the activation energy is so low that normal temperature, room temperature, is enough to get the reaction to go. Once the reaction is going, it generates its own heat and heats up the rest of it in exactly the same way that the methane does. So if we have our cigarette lighter and we light it, we can allow the gas to continue to come out and it will continue to burn. But if we mix methane with oxygen, it doesn't spontaneously catch on fire on its own, although this rate equation would tell us that it would go at a very, very slow rate. The other example that I like to give at this point is the transition from diamond to graphite. Diamond is the unstable form of carbon at room temperature and pressure, and so diamond should turn into graphite over time. The problem is, or the advantage is, that the activation energy is gigantic, and so this reaction doesn't proceed unless you heat it up considerably. About 2000 degrees, diamond spontaneously turns into graphite. It's obviously not a very useful thing to do, but it is an interesting consideration. The reason that that reaction stops on its own is that the amount of heat that it gives out is very small compared to the temperature that it needs, so you have to really heat it to get it going. This is what's going on with the energy of those two reactions. Stylized is not really the energy of those two reactions, but as we go along the reaction, we can see that our starting material, that will be the silane or methane, has to pass an energy barrier, which would be the activation energy here, before it can go down to form the products. And we can label the things on here. This is the activation energy up to the top of the peak, and this is delta H, the energy that we get out of the reaction, the heat energy that we get out of the reaction from the Gibbs free energy equation. There is a slight reality correction, as I mentioned earlier, because if we have a reaction that this equation would predict would go very, very, very slowly, most usually it doesn't go at all. That's because if we take a reaction like the conversion of graphite into diamond, to do that we have to move a whole lot of bonds, but we're only really moving 2 bonds per carbon. However, to start the reaction, we need to generate a new piece of new piece of graphite, and we have to move a whole lot of bonds initially before we can make any carbon at all, any graphite, and therefore the initial activation energy is higher than the continuing activation energy. It's a lot harder to start the reaction than it is to control it while it's moving. Likewise, if we take the silane reaction, losing the first hydrogen is the important bit in that case, and that is comparatively easy. We don't have to take the molecule completely apart, because the highest energy on our reaction profile is just one of them falling off, and in that case it turns out that it isn't very much more difficult to do that, because it's all in the gas phase, and once we've formed a hydrogen which has got an open bond, it can attack an oxygen and generate activated oxygen, which then goes and attacks the next molecule and so on. So it is comparatively easy, which means that some reactions stop completely or stop a lot more than we would expect, but only if we've got very close to stopped reaction anyway with the equation. That's because we are thinking of bulk conditions here, so we're thinking of a lot of material. We're considering it to be a continuum and not have any atoms in it, and when we go to single atoms, when we're making tiny amounts, then there are other considerations. Likewise, it connects to the other part that we had with the ice, where forming a new piece of ice costs surface energy, which wasn't in the thermodynamics equation. Here, forming a new piece of graphite also costs surface energy, which is not in this equation. This is a principle that's really important in chemistry and also in engineering. I've just put a few examples that are mostly everyday examples that you can think about. So if we take some glucose and we react it with oxygen, that's what we're doing in our body all the time to make energy. We make carbon dioxide and water. But if we take some glucose or some sucrose and we put it in a pot and leave it in the air, really pretty much nothing happens. That's because there's a very high activation energy. It's quite difficult for glucose to react with oxygen, and so it doesn't. But it's a reaction that goes very easily if there's some kind of way of getting over the energy barrier. In that case, usually an enzyme that helps to reduce the activation energy so the reaction can go at slightly warmer than normal temperatures. If we take an egg white and we heat it up, it turns into cooked egg white. It's a physical process, not a chemical process. The protein is rearranging. It is possible to get it to come back, but it's quite difficult. But this is a reaction that also doesn't go at room temperature. It has an activation energy and it's difficult to beat. If we change the conditions, so if we add some acid to it, for example, we can change the conditions and motivate it to do that. And beating the egg, for example, is also doing something very similar. We are mechanically stretching out the protein molecules, which causes them to fold differently, which is effectively a similar thing to what the heat is doing, although if we beat it, we get a slightly different result. If we take a glass window pane, it is a non-crystalline form of quartz. So it's silicon dioxide. They're both silicon dioxide, but quartz is a crystal and glass is not a crystal. The atoms in the glass are arranged somewhat randomly, not entirely randomly, but quite randomly, and the atoms in the quartz are arranged in the crystal structure. That means that the quartz can, or the atoms in the quartz can get closer than they can in the glass, which gives us some energy back. We get some bonding energy back, but the cost is obviously that the glass is more random, so we get some entropy from that. At room temperature, it would be favourable for the glass to turn into quartz, but it doesn't, because it's very hard for the silicon and the oxygen atoms to move around at room temperature. In reality, glass at room temperature isn't just pure silicon dioxide, it's got additives in it which also hinder it from crystallizing into quartz, because it would obviously be a bad thing if glass turned into quartz. There's a whole lot of technology involved in preventing it from doing so. Quartz has some good properties, but it's also hard to handle. If we take a similar example, so this is snow, if we take a snowflake, or a lot of snowflakes together, then we can keep them at below zero temperatures and nothing happens. They have the same disadvantage that we had before. They've got a very high surface area, so they've been formed in a way that generates a very high surface area. You know what a snowflake looks like. It's got a branching structure, very small. If we compress the snow very hard, then we can convert it into ice, so the snow recrystallizes into ice, and that reduces the surface energy because we've got less surfaces. We're compressing it to one crystal, and that allows us to get some energy back out, which is a good thing. But if we keep it really, really cold, we will find that snow doesn't do that. So if we go skiing, which is rare these days due to climate change, but if we do go skiing and it is cold, or we go somewhere where it really is actually cold, we discover that the snow doesn't stick to anything. Because the snow, even if we add pressure to it, is unable, the water molecules in the snow are unable to get enough energy to move around. The activation energy for changing their structure is too high. That is exactly the reason why our final law of thermodynamics, that if we have a perfect crystal at absolute zero temperature, that would have no entropy. That was the definition, but that is almost impossible to reach, because if you imagine if we cool something down and it freezes, then the molecules in there can't move anymore. And once they can't move anymore, it becomes very difficult to get rid of some excess entropy, some randomness that's in there. In this case, molecules that aren't in the correct place, or surface area that is unnecessary, because surface area also counts. Because we've got extra surface that's not needed, that's extra energy, and obviously to get to the lowest energy point, we have to get rid of all of that. With ice, it is comparatively easy to do. We can sit just below zero for a really, really long time to freeze it, and then we get a relatively big crystal. But for other things, it is impractical to get there. So if, for example, we have something that's made out of iron or steel, we are often in a state like glass or snow where we are not at the minimum of energy or the best entropy state, but we can't get there because kinetically it will take a very long time. In the case of glass, as I said, there are additives, so different things in there that make it unlikely to do that anyway. My usual example for this would be steel, because if we take steel, it's iron with carbon in it. There are obviously other elements in there, but we can think of the iron and the carbon first of all. If we heat it up, but it doesn't melt, we reach a temperature where the carbon dissolves into the iron, and that's fine. At that temperature, the dissolution of carbon in the iron is better because we are getting more back from our Gibbs free energy, because we have delta G is delta H minus T delta S, and our delta S is constant, but our temperature is now higher, so this term starts to win. It costs energy to mix the carbon in, but we get entropy back, and so if we get up to a high enough temperature, we can dissolve the carbon into the iron. What is more interesting is what happens when we cool it down, because we can either cool it down slowly, in which case the thermodynamics wins and it kicks the carbon back out, so the carbon and the iron separate again to the state that they were in before, where they both have a little bit of the other component in, but there's mostly iron carbide effectively and iron. But if we cool it down faster, then we end up with a state where it's trapped, where the carbon is trapped inside the iron, and it gives us a different type of material. It hardens the steel. That is very useful, but effectively we are trapping it in a kinetically trapped state, because we cool it down, and when it's cold enough, the carbon can't escape. We can also cool it down at different rates and cause different size particles to grow. So we can think of this as two parts of the same coin. The thermodynamics tells us two things. It tells us will the reaction happen, and it also tells us how much energy we could get out if it does happen, or do we have to put in to make it happen. And the kinetics tells us how fast it happens, and also has an effective temperature where it will speed up if we heat it up. There's a rule of thumb for the kinetics, because we have this rate is equal to A e to the minus E act over RT, and that's obviously difficult to calculate in your head. So there is a rule of thumb that says approximately increasing the temperature by 10 degrees will double the rate of reaction. So every time we increase it by 10 degrees, we will double the rate of reaction, because it is an exponential function. So it goes away very quickly. Because we're in corona pandemic times, everybody knows what an exponential function looks like these days. It used to be an uncommon thing to know about. An exponential function is a kind of curve, very much like a squared function, but it's a little bit flatter on the bottom. So this would be the rate, and this would be the temperature. Finally, we'll talk about what the rate is. This is a different reaction that I'm going to use to explain this a little bit better. So we've got carbon, solid, plus oxygen gas, and that is reacting to form carbon dioxide. The reason that I've chosen this particular reaction is that there's one molecule, and one molecule, not one atom, one molecule and one molecule, because it makes the numbers easier. When we're thinking about the rate of it, we want to know how quickly carbon dioxide is being formed, or how quickly oxygen is being used up, or how quickly carbon is being used up. And in this case, because it's 1 to 1 to 1, they're all the same thing. So we want to measure that rate, and we will measure the rate of production of carbon dioxide, because it's then positive and we don't have to worry about signs. So we have the amount of carbon dioxide. In chemistry, we like to put that in brackets, because that stands for concentration or amount. So we want to know the amount of carbon dioxide being formed per unit time. If we know that, then we can call that the rate. But how can we define that with a mathematical expression? We can do that by using school maths. We can call it the rate of change of concentration or amount by time. D carbon dioxide dt, the rate of change of carbon dioxide per unit time. You will be familiar with that probably from maths, from integration and differentiation. It's the differential of the amount of carbon dioxide with respect to time. What does that mean? It means it's the slope of the curve of the carbon dioxide amount, because that's what the differential is, which is the rate. That's very handy because it allows us to understand it somewhat better, and it allows us to use that other equation, the Arrhenius equation, if we define this as being the rate. That's obviously equal to minus the rate of change, minus the rate of change of oxygen per unit time. The difference between d, little d, and delta is that d is instantaneous, we're measuring the rate at an instant, and delta is the rate of change over some amount of time. Big delta, this triangle one, is over a longer time, the total change. In this case, because we're measuring rate, we can measure the instantaneous rate, or we could measure the average rate, which would then be delta. Usually we're interested in the instantaneous rate, but practically if we measure it, we have to measure it over some amount of time, so we're really measuring delta. Just to finish off, we'll just check the units in this equation. So the rate is in moles per second, let's call it per second. That's going to be equal to a constant, A, which we don't know what is, multiplied by e to the power of E act, which is going to be in joules per mole. Let's call it mole, because we're going to use R, so we have to use joules per mole, divided by R, which is joules per Kelvin per mole. That's the standard for the ideal gas constant, and then we're multiplying by Kelvin. We can see here that the Kelvins cancel, and the joules per mole cancel. Sorry, I forgot the negative sign, but it doesn't matter because it's also cancelled out. So we end up with no units there, which is really handy, because if we have e to the power of something with units in, then we end up with some problem with units. Now we've got rid of all of the units, and so this A has to be in moles per second. This principle, or this effect, is very common in chemistry and material science, but it's also common in other parts of life, and so we can see that very often we are controlling processes by either controlling the speed or by controlling the thermodynamics, or both, and very often we are controlling the speed of things and trapping them in a state where they can't escape, and one that they're not in their lowest energy state if we want to get energy out later. And very often we might want to change the conditions, so making ice, we change the temperature to freeze the water. If we want to make something and make it permanent, we would like to make it thermodynamically stable, but practically most things are not thermodynamically stable, they're kinetically stable. So a bridge, for example, made out of iron or steel is not thermodynamically stable because the iron should turn into iron oxide. However, it takes a really long time to do so because we treat it with paint and all kinds of things to make it kinetically stable, to make it very difficult for the iron to turn into iron oxide and break our bridge.